And so I want to show that this thing is small, and there are basically two strategies for showing that this is small. And I think these are the two basic strategies in this thermalization business. And one is eigenstate thermalization hypothesis, and the other is large effective dimension. And let me explain these two things to show that this is. And energy eigenstate thermalization hypothesis, this is very simple. In this version, I assume that for each j, this average of P net with respective energy eigenstate itself is exponentially small. This means that each energy eigenstate psi j in energy shell represents thermal equilibrium. And this idea again goes back to von Neumann, I think. And of course, you have to be careful. There are many different definitions of ETH depending on how one formulates the notion of thermal equilibrium, and I think you can hear from this about that. Yes. And anyway, if you assume this, then of course it's just trivial. Each of them satisfy this inequality, so of course the average also satisfies this inequality. So if we make this assumption, this is a very big assumption, but if you make this assumption, then you can prove with this assumption theorem, which says that for any initial state in the energy shell, any state, phi t represents thermal equilibrium for most t in the long run. What do you mean by for most t in the long run? Well, this is a more precise statement. It means that there exists a large constant tau, time scale tau, and the subset B stands for that, of the interval from 0 to tau. But this B is minority. If you look at the total length for the big measure of B divided by tau, it's exponentially small in volume. And B is bad in the sense that if you take any t from this green bit, which is in the interval but not on B, then you certainly have that your phi t represents thermal equilibrium. This is exponentially small. Since this is quantum mechanics and everything oscillates, you can never expect an exponential decay or total decay to equilibrium, but we can prove and expect this kind of decay. So this is one thing you can prove by assuming this very strong assumption. And the result is very, very strong and very nice, but I don't know. But and this covers any initial state, even preparable or non-preparable or whatever. So this is very nice, but I would just, I don't know. But probably may not be necessary to cover any initial states. And well, I'm just saying this, but it is extremely difficult to verify this assumption. And I don't know any non-trivial example that we can prove. Of course, we can cook up many toy examples where this can be proved.
You said that B results to some extent because the system is quantum mechanical, things are oscillating, we can't expect something to decay throughout time. So is it a separate problem of having a finite size system that would have recurrences, and I think of the recurrences as times also at which there's a lack of this nice equilibrium? Would that be something a bit separate from B?
I think that so the recurrence can mean many things, but yes, in this sense, what I meant is precisely the recurrence. Okay. So everything is just oscillating. So if you wait for a very, very long time, you will see something very close to your initial state, and that is recurrence. And of course, with this recurrence, you can never expect that. Okay. In this form, a very formal treatment of totally isolated systems. Okay. Right, so this is the strategy number 1, energy eigenstate thermalization hypothesis. And the strategy number 2 is slightly more complicated, but that relies on large effective dimension. I mean, it's simpler in some sense, but still it has many problems. And, okay, so this is initial state, and I show that I wanted this guy to be small. Okay? Initially, this guy is not small, but after some time, I want this guy to be small. And I take the long time average, and this became this diagonal average. Now here, I use Schwartz inequality. This thing to get this. And since this is less than 1, you can just drop this square here. Then this becomes a trace in the energy shell. So you get this formulation, expression. So let me write long-time average that I want to show that it's small is bounded by this times this. So let me look at these two parts separately. First, this one. I first define something called the effective dimension of the initial state phi 0 with respect to h. And this is, it's defined by these people. And it's defined like this. You just, if this is 2 squared, and then these things sum up to 1. But you have 4 instead. Okay? And then you can easily convince yourself that this counts the effective number of energy eigens which contribute to this expansion. Why? Well, if suppose that only one of them is 1 and all the others is 0, then you are just summing up 1, 0, 0, so you get 1, inverse is 1. Okay? So in that case, you get 1. And also, if you suppose that all Cj are like 1 over square root d, and you compute, then you find that this is d. So this is roughly the number of energy eigenspace corresponding to the effective number. And so I use this for this part. And for this part, I observe that if you divide this by d, then this is nothing but the microcanonical average, and this is small by thermodynamic bound. So if you plug this in, this and this into here, you find that this long time average is bounded by, first of all, exponentially small thing, and this ratio between 2 dimensions. And this is greater than or equal to 1, but if this is small, if this is not too large, then this guy wins, and you will see that this is exponentially small. So my wish is that this guy is larger. And there are some arguments, Occam's argument that it's large. But anyway, let me summarize. So in this second approach, the assumptions are that there's no degeneracy, no thermodynamic bound, and they can be proved in several complete models. And this is a difficult assumption, that initial state satisfies this bound. The effective dimension of the initial state is not small. And this means that, roughly speaking, if you expand initial state in energy against state basis, these coefficients are sort of mildly distributed, not sharply concentrated on some points. So this looks like a natural assumption, but of course it turns out to be a very delicate assumption. Anyway, for any initial state phi 0 satisfying this, satisfying this, phi t represents its Hamiltonian, phi t represents an equilibrium for mostly in the long run. This can be proved. There is a mixed state version, but that is just trivial, so I'll just skip. So this is a rough summary of how do we get there part. So a pure state evolving under the unitary time evolution can thermalize. That means represent thermal equilibrium for mostly in the long run if 1. ETH is valid. 2. Initial state has a large effective dimension. And so this is a rough answer to, this is sort of mathematical answer for justifying this rough picture. But still, there are two very non-trivial assumptions here. So this is very difficult, and I have almost nothing to say about. So let me talk about this second approach, the large effective dimension. Now I want to discuss whether when it is large or when it is expected to be large. But this part is very, very primitive and incomplete. At some say I was rather optimistic about this approach, but I had a severe criticism from Takahiro-sagawa and I'm less optimistic now. But anyway, let me try. So first of all, let me state my old wish. This is not really a conjecture. This was a just last wish. For most realistic Hamiltonian, I don't know what it means. For most realistic Hamiltonian or macroscopic system, most easily preparable state, initial state, this energy density U has an effective dimension D. Effective, not much smaller than the whole dimension D. And this is just what we want. And then this initial state thermalizes. So if this is true, then we can show that, okay, if you have a good initial state, it thermalizes. But of course, we still don't know how to characterize easily preparable states. But anyway, we know that, it's just impossible to prepare any state in the energy shell. Some of the state in energy shell is really hard to prepare. But for example, the product state or the Gibbs state of a different Hamiltonian matrix product state, which was originally called finitely correlated state in one-dimensional smooth chase, are, I think, examples of easily preparable state. So my first hope was to show this kind of statement for this kind of problem. And this is not true, but there is a theoretical support. This is wrong, but anyway. There was an argument which first looked as a support for this claim. So let the initial state, I'm now talking about the mixed state, but this can be initial pure state too. Let's take a state which is sufficiently disordered, like a product state. In that case, it can be pure, or a Gibbs state of a different Hamiltonian at sufficiently high temperatures. And in these cases, usually you can use something called Quantum Central Limit Theorem. Some of you are more familiar than I am. And in this kind of state, if you look at the distribution of energy, H, then it converges to the Gaussian for large volume. So this means that if you look at the energy distribution of energy in this state, this disordered state, it looks like this, Gaussian, centered at UV. And this width is order of order UV. Yes.
Do we have any other condition for quantum central limit theorem? I say for any physical system?
There are. I forgot. But if you are, I'm sure that if you have Gibbs and it's sufficiently high temperature that any correlation decay exponentially, then you have this. Well, I think that you have this for products.
So, sorry, what is leader? I mean, forget about it. What is locate leader? What is leader? What is the leader for locate?
What is the
leader? I forget.
Rho zero. I'm sorry. This is initial state.
Oh, initial state.
Yeah.
So this for any initial state we can have a quantum central limit theorem.
No. So I'm saying that if you take a disordered initial state.
So I said the associated state locate the leader. So I mean that only for initial state you could find the quantum central limit theorem.
No. I'm sorry. Yeah, this is confusing.
Oh, yeah.
I'm saying that, okay, suppose that you take your initial state as I'm thinking about like plunge. So you prepare your initial state as a Gibbs state of some other Hamiltonian. So it means that you fix your Hamiltonian and you let it thermalize. And then at time t equals 0, you suddenly change your Hamiltonian to this one. That's what I'm assuming.
Is this also useful for field theory? For equally dimensional Hilbert space? Is this also useful for field theory, quantum field theory? I say because in quantum field theory, the dimension is Hilbert space, so it's not always correct for the mathematical proof. But could we check it?
I don't know. I mean, field theory is really difficult. You have to
because when you talk about field theory, this does not have mathematical proof. Because when we use mathematical proof, we need to assume that the dimensionality of Hilbert space is finite.
This is mathematically this is only for lattices. For a sufficiently large group.
Okay.
Yeah. And I think in the proof, they make use of the lattice form.
So this means that the lattice Young scale is maybe correct because it's measured compact at a distance.
Let me think of it. Okay. Anyway, so this is Gaussian. And the radius is square root v. And so if you count the number of energy eigenstates sitting here, then you find that it's almost equal to d, the whole dimension. Then it's Gaussian distribution. There are almost d states here, and this means that almost d states are contributing to this expansion. So you have d effective almost equal to d, and we are done. But of course this is wrong. There are many counterexamples that there's no thermalization. So we have to think about this. But this was sharply demonstrated partly by numerical work by Marcus Rigel last year. And he found that if the Hamiltonian H is integrable, then d effective associated with disordered initial states is much smaller than the 4-dimensional d. It's exponentially smaller, much smaller. So my wish is not fulfilled. So my conjecture was wrong, totally wrong in this case. But we understand this quite well because in integrable system we have many extensive conserved quantities. And Quantum Central Limit Theorem or Quantum Large Deviation Theorem tells you that in this disordered initial state, density of A's are almost fixed. And this sort of tells you that the effective cannot be fully equal to D, but it should be exponentially small, unless these A bar take the precise equilibrium value for the corresponding equilibrium state. So what happens to the Gaussian? What happens to the central limit theorem? Is it wrong? Of course it's true. But what central limit theorem tells you is simply that if you sort of coarse grain and look at the energy distribution, it's Gaussian. But if you look at it closely, then it's so sparse. And only very few number of energy eigenstates are occupied, and there are many billion vacancies. But anyway, still it converges to Gaussian. So this happens to integrable system, and I think this also happens when you have many body localization. There are many conserved quantities. So this bothers us from having large the effective dimension. And according to Marcos, if H is non-integrable, then the distribution is dense, and one has the effective which is as large as. But this is at least numerically for some models, and I don't know if this is true. But if you believe in Marcos, then I can refine my conjecture. For a non-random, non-integrable Hamiltonian over macroscopic system, most easily preferable initial state means something where the central limit theorem holds with energy density U. This has an effective dimension not smaller than the D and thermalizes. But this is just a refined conjecture which avoids obvious counterexamples, but who knows this is true. So numerical works are not yet conclusive, and Takahiro is very critical about this conjecture. I don't know. And anyway, I'm basically a mathematical physicist, so I want to prove theorems, but it must be extremely difficult to justify this rigorously. And we only have very partial results. So this is one of the partial results. There are many partial results and many cooked up examples, but this is one of my cooked up examples. For this case of two bodies in contact. Okay, so I have two Hamiltonians with non-degenerate energy eigenvalues, H1 and H2. They are identical and they are interacting. And I diagonalize this H1 and H2 like this. This is just possible. And then this is, I'm ashamed of this, but this is just a really tiny. I cooked up my H interaction like this. H interaction acting on the tensor of psi k and eta L simply changes these indices only by 1, plus minus. So it produces only 4 states with some coefficients. And don't ask me what this is. This is just a term. And then with this I can prove the following. Psi j is the energy eigenstate of the whole Hamilton. And you can always expand this using the tensor product of these two, psi k and L basis. And so this is true. This is always true. And I can prove in this case that this coefficient C are dominant and almost comparable for KL satisfying this one. Well, what is this? Well, this is rather, I think many people agree with this. This is natural. Suppose that there's no H interaction. Then Ej is precisely equal to Ek plus El. Because
how do you mean for Ej minus epsilon k plus epsilon L? Do you mean that for each j is larger than each k and each L? Yes, because the index is different.
This one?
Yeah, because the index is different. So Ej minus, you do not say epsilon j because epsilon k. How do you mean?
No. For a given j.
So for each j is larger than.
For a given j,
okay.
There is a set of k and l.
Oh,
determined by this condition.
The distance of k and l.
Yeah.
Okay.
J is fixed, and you say that KL satisfying this inequality. And I was saying, okay, if there's no interaction, then then this is simply the tensor product. So Ej is equal to Ek plus El. That means epsilon is 0. In that case, KL satisfying this is unique, just a unique.
Okay.
But now, if you add small perturbation, and then these states will sort of mix up. And if your perturbation is magnitude epsilon, probably you expect that it mix up with the epsilon. So, no, I think this is quite a natural thing that you expect in this kind of perturbation. So, well, but in my case, I had to write this down to prove this, but I think many of you agree that this is a natural thing to expect. But anyway, if you have this, you can prove that the effective is almost D for example, initial state, kind of natural, easily predictable initial state, which is the Gibbs state, the tensor of two Gibbs states with different temperature. And in this case, I can show that there's thermalization, means that energies are not distributed unequally in the initial state, but after a long time, they will distribute it almost equally. Oh, by the way, so this is entanglement. So, this means that entanglement in the energy eigenstate between the two states, two systems, probably almost the maximum entanglement possible within the energy conservation helps the thermalization. That is the message of this Dorian example. Okay, so this is my tentative summary. So what is thermalization is a question, but I would say it's a typical property of state in the energy shell, and more sphere state represents thermalized later. How do we get there? This is that question, I think. And this can be proved by making very non-trivial assumption, ETH or large effective dimension. So there are many questions that remain. But can I go on? I have some more. There are some more questions. So this talk was done, but let me talk about one related issue, which is related to an open problem of time scale. And this is an approach which goes back to von Neumann, and I think it's not very physical, but anyway, it's something interesting. So this is von Neumann. This is something I call von Neumann's random Hamiltonian approach. Let H naught be some fixed Hamiltonian, and H shall be corresponding energy shell, the same thing as I did. And I again pick my macroscopic quantity of interest and corresponding non-equilibrium projection. That's the same as before, but I take random unitary operator chosen according to the Hal measure on the energy shell. Then I apply this random unitary onto this fixed Hamiltonian to make a new Hamiltonian. So since this is unitary, this H has the same spectrum as H naught, but its direction is totally wrong. It's really wrong. And von Neumann proposed to use this. He said it in slightly different way, but he proposed to use this H. So the energy eigenstate of this is written like this, and time evolution is determined by this random H. Well, this is rather brute thing to do, but anyway, he thought about this. Then, first of all, with this approach, you can prove, he proved, von Neumann proved ETH, energy state eigenthermalization hypothesis. So it's not a hypothesis in this approach. It's probability very close to 1. This probability is with respect to the random choice of the unitary. This probability very close to 1, exponentially close to 1, this is for any G. So, if you are given one J and you are asked to show this, it's just a very easy problem. But in this case, you have to show this for all J at once. So it's not an easy problem. But anyway, you can do it. So one thing, ETH can be proved.
What do you mean by U is random?
It's a hard random. So H shell is a d-dimensional space. So you take totally random. So Hal measure on this d-dimensional unitary space. So it's a pure Hal random.
Sorry, so the U is completely defined. So there is only one U.
You throw your dice and you pick your U.
And once you pick one, you use that for anything.
Yeah. You use it. You use it all the time. So this is hard to do. You pick your one, and once you pick your U, it's probably very close to one this thing.
Suppose what I pick away is U equal U is just the identity matrix.
Oh, but yeah, but that's very rare. So yeah, then it's explained by this story to very close.
Oh, I see.
Okay, anyway, this is probably the state.
Sorry, but forget about this. But
yeah.
So after this random unit, is this H still local?
Oh no, it's totally non-local. So I think that's a point. It's really non-local, more non-local than black hole. So I think yeah, that's the function. So I think this means that von Neumann is too non-local, and you will see. Okay, so by this two non-locality can be first found in this theorem, which I proved with Shelly Goldstein and Takashi Hara 2 years ago. And it said that it thermalizes, everything thermalizes within this very short time. So we can prove that up to some tau for any initial state. So this, again, this happens to probability very close to 1 for the random choice of U. And we can prove that any state thermalizes like this. And this means that any initial state thermalizes in the time scale of order the Boltzmann time, which is h divided by kt. And this time is very short. If you are in 300 Kelvin like we are, then this tau is 10 to the minus 13 seconds. So this proves rigorously that everything thermalizes within a microsecond. Your coffee is no longer hot after a microsecond, or you're totally dead after a microsecond. Of course, this is totally against our experience. So sometimes you see some quick decay, and Peter Riemann is working on that. But anyway, usually this is unrealistic, too fast. And also, you can go on to compute something fashionable, which is called out-of-time order collider. I think many of you are familiar, and we will have a talk on this. And let W and V be arbitrary operators, and this be microcanonical average. And unlike before, bar denotes the average of random U, random Hamiltonian. Okay? Power measure random. And we expect that this is equal. If we work hard, we can show that this is a typical value for collider. But anyway, if you average, you can just compute this thing explicitly. And we are told that if you look at this kind of correlation, it's boring. But if you look at this kind of weird combination of correlation, then it gives you something interesting about quantum chaos and reasons of here. But anyway, if you do this computation in this von Neumann's formulation, the result you get is boring. And all the time dependence is expressed by this single function phi t, which is simply just the sum of these exponential oscillating terms. So in typical case, this is a typical density of state you can think about for system of temperature beta. This thing can be written explicitly, but anyway, this form is not interesting. The only thing, this tells you that the only time scale coming in this business is h over kT. And nothing very interesting happens if you do this computation. And so the summary to von Neumann's random Hamiltonian is that you can prove ETH, well, that's nice. But in this case, if you look at the time evolution, the only time scale is a Boltzmann. And this, I think, captures only limited aspect of time dependence. And as you said, I think the reason is that by applying this random unitary, the new random H becomes really non-local. And I think it's not only non-local, but it probably contains really many body interactions. So I'm sorry to von Neumann, it's a clever approach, but I think it's too much to do. So this is something I already showed. This is my summary, and thank you very much for attention. Many inspiring questions. That's very nice.
So if we change the random distribution for the unit version equation,
What did you say?
change the random probability
Ah.
for the unitary transformation, then will we get better result?
Yeah, that's what we were thinking, but it's very hard to treat. Yeah. So you can think about some. You can think about some random unitary which preserves locality, or Please tell me if you know anything. That's very difficult. This how random is just stupidly. It's still needs some technique, but it's easy because it's just a random unitary. You can use all these knowledge from back to lattice stage theory and things like that. Yeah. So we use something called Weingarten formula. Weingarten is a name if you know lattice stage theory.
I wonder, decades ago, Hayden and Tasaki had an interesting idea involving k-local unit traits on quantum channels. Patrick Hayden and Deff Let. They were mostly interested from a quantum information perspective, but part of their motivation also came from talking about black holes. And in this context, there are various conjectures, some of which you probably know go by the name of fast scramblers, of identifying some kind of Boltzmann time as sort of the right time scale for black holes to thermalize. I was wondering, which is also what this out-of-time order correlation was re-inspired by recent work. I was wondering if, given this statement from von Neumann, we don't have at some intuitive level we expect that black hole physics is also governed by effective locality, whereas what governs the fast relaxation in that context is sort of strong interaction. You have something complementary to that where you seem to see fast relaxation, but in a context where you basically just immediately interact with everything in one go. Is there something that one can say in some intermediate context?
I have no idea, but anyway, so they say that this black hole scrambling is the fastest thing in the world, but probably this is faster, I think. Because if you look at this, Kitaev's model, this one, right? But anyway, it's a long range model, but you only have few body interaction. That's still healthy. But as you said, in this case, we are just doing random unitary, but just stupid. So even if you started from a very nice Hamiltonian, you just do the real one. And you're generating not only non-local, but you're probably generically if you have n spins, I think this contains n spin interaction in general. That's just very, very obvious. And I think that's a reason that we have very simple structure even for decay and also this OTO correlator. I'm not very familiar, but I couldn't compare this with what's written in the recent fashionable papers, but this is very simple. If you're interested, then you can compare, and you will see what is missing here. And I think that will tell you what's the role of two-body interaction.
So from this many-body physics point of view, we usually that's the locality, right? So that means any kind of random still has no chance to locality, and this must be local interaction. So in this case, I think there's also some notion of the Robinson bound. There's some additional
of course.
Still, so do you have some explanation with those local units, random local units?
I have no idea how to use random locality. But anyway, you know that this is really quick. But if you have a short-range Hamiltonian, then you can use Lie Robinson bound, of course. Then you can have sort of lower bound for relaxation time because it's just trivial. If you do something wrong here, you have to wait for this wrong thing to propagate. So the application of the Lie Robinson bound tells you that your relaxation time should be at least larger than the system size times the constant. So this certainly violates this. So but I don't know what we can do. But for the moment, if you think about Lie Robinson bound, that's a trivial application. But the trivial application says that the relaxation time should be at least the size, at least linear in the size of the system.
But that's some kind of physical reality or physical constraint.
Yes. Do you know any way of treating random local thing? Because it usually makes the problem difficult, making it in a random system. So in this, for Neumann's case, you can rely on Hall randomness, and many formula becomes easy. So that's why he used this.
Actually, there's some more, but a quantum central limit. So they have some unitary, but it is more restricted. It's not for always mapping local operator to local operator.
Is it true? Yes. Okay, I want to learn it.
I have a very primitive question. So sometimes you mention this ETH is hard. I assume you mean it's hard to prove, right? Generally. Yeah. But I want to ask, so are there like counterexamples? Like a system circularized but don't satisfy ETH? This.
I think that is possible.
But are there counterexamples like that?
For the moment, I think there's no counterexample which I can tell you. But I think that is just possible. That, you have, most of the energy eigenstates are nice, but you have if you have one or two exceptional ones, then the ETH in the strong sense is viable.
I have 1D many-body localized states are counterexamples.
Oh, of course, but they don't thermalize. So his question was, it thermalizes, but still fails to satisfy.
Similar to colorful subdivision, but somehow violate ETH.
But
Just curious.
yeah, but even in case of many-body localization, it depends on what your initial state is. So, so even in many-body localization case, if you pick your certain initial state, you may have thermalization. So that's, the question is very subtle. Of course, we cannot go on forever.